Okay, so we're going to talk about a few things here. Mainly, what we're going to talk about is 3D printed mold forging specific to TPU, a thermoplastic urethane. And I guess it's probably good to start with where I got, or how I got here. So for the Prelude SH, it's got a radius rod bushing that is usually rubber, but I wanted to make a spherical one. And the problem with doing that is if you put a ball joint on this side, and that has a ball joint on that side, even if the center of mass was directly between the 2 points, you're still kind of unconstrained, and so you'll get kind of a notching on the ball joints. The center of gravity of this arm is not in the center of axis, so what's going to happen is this arm's just going to swing around as you're driving. It will wear out the ball joints more. It'll cam them out, as we call them in the bushing industry, or the ball joint industry. And so my solution was hey, what if I could put a bushing in here just for torsional rigidity to keep the arm oriented, to constrain that free axis of rotation. And so what I came up with was, hey, I could 3D print these polyurethane. They're a 95A is pretty typical. You can go down as much as I think 55. I have some 75 stuff that's pretty soft. But what ends up happening is it looks not great. You can see through it. I don't know if you'll be able to see it on the camera, but you can kind of see the voided space on the inside there, right? And so, A, this looks terrible, and B, it's not gonna fatigue very well because this is basically just full of stress risers. It's like, okay, well, this is cost efficient, so I went to see how much it would cost to get these cast. I could cast them myself, but time is money, and I plan on selling these. And so it wasn't really at a good price point to cast them. And injection molding, you're going to spend $2,000 to $3,000 just on a mold to make this in injection molding, plus you'll have to order hundreds of them for the piece price to be okay. So I said, hey, what if I can take a thermoplastic urethane and a 3D print specifically and post-treat it in a way that you get an injection molded quality part. And the reason you want that is that basically it's a mold, and then you heat up the urethane and you shove it into the mold at a really high pressure and let it cure, and then you spit it out and do it over and over. And so I'm like, well, you just need pressure and heat, right? And so I decided to make some molds. And the way this mold works is you take your 3D printed boot, you shove it in there. This guy's a little torn up from evaluating stuff. And actually the hard part of the mold is figuring out the right way to make it so that it works. And so you have to be able to take it apart in a way that you don't destroy the new part when it comes out, while also getting kind of a good normal force, equal pressure on all the surfaces. And so for this one, this is what I came up with. And so there's a cutout on the inside to fit basically all of this. And so you put the mold in there, and then to be able to take it apart, all of these got to be able to fit, right? So you can't just put a ring in here, it'll get stuck. And so I've got these to kind of offset that gap. And what's nice about these is they're angled, so you can just slide them in. And you don't have to have it perfectly aligned. You can just kind of wedge it in, and it creates a pressure as you wedge it in. So the tip starts nicely, which is nice, and then you can just push it down in there. This is the outer piece that holds those into place. And then lastly, the inner piece just goes in. And then you bolt it together between some metal, and you throw it in the oven. Now, when you're engineering any solution to anything, you have to ask yourself, what are all the problems that could arise? And how do I develop a robust procedure to those? And so there's a lot of issues you get when you do this. Is you have to compress the material. What's up, Frankenbeans? And to compress the material, you have to over mold or overprint the final product. And so for some simple geometries, you can import into the slicer, and you can just set grow the part by X%. I will say for this model, for ease of assembly, I grew it in the Z direction, probably about 4 to 5 times more than I grew it in the XY. And that seemed to work okay. But what happens is with more complex shapes, and especially this one, just a simple grow may not be what you want. So I do make sure that my 3D files for the models are what they represent in like what the final product is going to be, and then I do my geometry changes in the slicer, with a few exceptions. The interference fit between this and the part in real life. And so one of the things to consider is I want this to stay retained at all angles, right? So I don't want it popping out. I don't want the seal breaking. And so I had to do a couple things. I had to make this outer diameter larger than the inner diameter of this so that it would push against it. I also had to make it thicker than the gap so I could feed it under and have it under pressure so it's less likely to slip. And then I kind of did a similar thing with this inside. I made it much smaller, so it's very difficult to install these, but it's also difficult to remove them. You can see there's an undercut for the inside of the boot to kind of fit in there. And so what I was able to do was, after you forge these, they are perfectly homogeneous. They look the same all around. If you cut it open, you no longer see, there we go, you no longer see holes and stuff in there. It's fully homogeneous. And not only is it homogeneous, but it's cured under pressure. And so a way that you can figure out how to grow your volume is, you look up the compressibility of the material you're using, and you look at initial volume versus final volume and figure out what pressure it has to be under to reach those volumes. And then if you reference typical injection molding pressures, you can actually pretty simply calculate what it is. Now, it's going to be different for every material, and I'm not going, I spent a lot of work trying to optimize this, so I'm not going to share those secrets, but it is pretty simple equations. If you're going to do this and you want to do it correctly instead of just giving it a go, which is perfectly fine, I did a mix of both. You just compare the compressibility of the material and the initial and final volume. The one thing that's going to be a flyer, which is kind of the secret sauce, is to figure out how much air and voids and gaps is inside this, because if this was injection molded under zero pressure, you'd end up with more volume than it comes out in the print. So that's kind of what you got to account for. Why did I decide that using thermoplastic polyurethane was better than using a 2-part cast polyurethane? There's actually quite a few reasons for that. Thermoplastic urethane does have a higher yield strength. It has extremely high elongation. We're talking like this 95 durometer stuff, or not durometer, 95A stuff. It's got an elongation of like 700%. So like, you can stretch this to 7 times its length before it breaks. You do that with cast polyurethane, it's going to rip. Especially if you already have a crack in the cast urethane, it will rip. Its shear modulus is not as good as a thermoplastic urethane. The other thing is, I'm not sure if it's in my car, but I've got melted polyurethane engine mounts. Because when cast polyurethane gets hot, it doesn't recrystallize. The beagles are fighting outside. Yeah, whatever. And so the nice thing about this stuff is you can melt it and it comes right back. So it's stronger, it's durable, it's stretchier, it's better with heat, and it's got about the same operating temperatures as cast polyurethane too. So that's why I did decide to go down this rabbit hole, because for me, TPU is a superior product to cast PU. Not all of them, but for the stuff that's easily available. And while it does take a while to print, I don't have to be there. For a quality cast urethane part, it's hard to do in large batches. You've got to mix up however much you need, and however much you need, you have to be able to pour usually within 10 minutes. So it has to be poured within 10 minutes or it'll start to harden. And so in that 10-minute gap, what you've got to do is you've got to mix it, and then you've got to vacuum out the mixture to get all the air bubbles out of it. So you got to put it in a vacuum. And then you have to pour it into your mold. And a lot of people will put it back in the vacuum just to make sure that they pull the air out from the pouring process. Some people will skip that depending on how complex the model is. And after you vacuum it out, then you have to put it in a pressure cooker, essentially, an autoclave. And you can pressurize it with, whatever you have. If you got an air compressor, 150, 250 PSI, whatever, that's good enough. But you have to compress it and bake it to do it properly. Yes, you can just pour it, mix it in a container, pour it in a mold, and let it cure, and that's fine. But I'm trying to make products that are durable and have, as OEM of a fit and finish as you can get. On the contrary, I can hit print, and I just need material in there, and it'll go for 12 hours straight. And then when it's done printing, I take my molds that I've already printed out, and I stuff them in and bolt them together and throw them in the oven overnight. So it's a long period of time, but it's not a ton of actual labor in the middle. And you end up getting a really nice, high-quality part that has a nice frosted finish, which actually looks really nice. But testing this material, so if I print and forge rods of these and test them against a good rated polyurethane that I have a tech sheet for from McMaster, the numbers match pretty well. So I guess the numbers you'd expect to get kind of match. So it supports my thesis that this is a good material. And so far I'm pretty happy with it. And so that got me these boots. And what's great is not only do they prevent the arm from flopping around, but they just genuinely do make a good seal and keep debris out. So, and they look sweet. I'm pretty happy about that. I'm going to get into talking about these engine mounts, or these transmission mounts now, since I do have some more stuff to talk about in regards to the mold, but we can move on to the transmission mounts. So, somebody reached out to me and said, hey, there is a car called an Acura CL Type-S V6 with a manual transmission. They only made 3,000 of these, I think, in the US, and I think 300 in Canada, maybe. and it's a pretty cool car. It's a 3.2 VTEC, manual transmission, but they can't get mounts for them anymore. They can't get replacement bushings. Nobody makes anything. So I said, hey, what's your budget? Are we talking $100 a mount, or could we go up to $200 a mount? And so we did kind of a feeler on the Facebook group, and you know, people are like, hey, the people who have those cars are extremely passionate about them, and they want to buy good quality stuff. It's a really cool group. And out of the 3,000 or 3,300 made, there's something like 17 or 1,800 people on the Facebook group. So it's most of the owners of those cars are on the Facebook group, and you can imagine not all 3,300 of those cars are still running. So it's a pretty cool community that they have. And so they were like, hey, give us a few options, and we'll go from there. So I said, send me the mounts and we'll get started. So they sent me these mounts, and here's the bushings, and they're stamped steel mounts, pretty cheap, pretty basic. And I was like, yeah, I can definitely make this work. I can probably come up with something. And so this is one of them, and here's the other one. And so one of the questions was, well, some people were like, obviously not everybody is going to want to pay, $350 to $400 for two mounts. Some people just need new replacement bushings. So my goal was to make replacement bushing cans and an inner metal, so you could just press out the old bushing and press in the new bushing into your OEM mounts. And so that's what we have here. So some of the problems I ran into here, I guess we'll go through the evolution of the bushings, and we'll start there. So I had to come up with the design first, and what I did was I stayed in the exact same packaging space. So I did not go outside of the packaging space in any way. And honestly, there are places I definitely could have cut down. And so I showed these renders, and the feedback was super positive. I think within 24 hours of setting up the group buy, or not the group buy, but I guess the interest list of people who would want to be on a group buy eventually, there was about 30 of them. I woke up the next morning. I was in Italy at Ferrari for the first few months of this year for my job, and so it was nice to have something like this to work on while I was over there, so I could kind of keep the business moving a little bit. And the feedback was really good, so it's like, all right, so let's get started. And so, the billet's the easy part. I 3D printed some prototypes and shipped those to one of the guys who originally set this up. And he checked them out, fitted them, everything was good, except I got the thread pitch on these wrong. I just assumed it was M10 by 1.5, because that's super common, but it was M10 by 125. And I did want to go with stainless if I could, and so there's not a ton of really quality, high-strength stainless steel bolt options, or even a really good threaded rod, because I don't have a really good setup for doing high-quality threaded rods here. It just is what it is. I'm sure I could come up with something, but I'd rather just buy something that's ready to go. So I didn't do that. I bought something that's not ready to go. But I got a pretty high quality bolt. These are very high strength. It's a good stainless. And for these mounts, I made them look a little bit nicer. I originally wanted to use a button head, but I couldn't get a quality button head in a high enough strength, unfortunately. And so yeah, I make those look nice, and then I cut them down and machine the tip so the tip looks really nice. And that's kind of a big pain. I got to figure out a way to make this a little more efficient, because this is not a good use of my manual time. I probably will just have my machine shop spit out a bunch of these. I'm sure it's worth the cost at this point. And so this one, straightforward, just one solid billet. I did want to try to do this in solid billet, but the price just is going to skyrocket, because it's such a larger chunk, and this piece can be made in a lathe. So you might argue, well, making two pieces is less work on a CNC machine than one, but as far as time spent, most of this is done on a lathe, so your material is a lot cheaper, and then you go in with a mill and make the pretty parts in the end, and then you bolt these together. So we've got 3, again, super high strength stainless steel bolts here, and another one here. I believe they are all M5s, maybe M4s. I think M5s. And they're pretty strong. I could have just welded these together, but I think the idea is once I get a bunch of these in, that my girlfriend, for example, can just grab a bunch of these and assemble them, even though welding probably won't be difficult for her. And of course I have to put my brand, my logo on everything. So yeah, I'm pretty excited. These should hold up. There's way more material than this really, really thin stamped steel, so I know if my stiffness is at least better than OEM, then I'm good to go. So the difficulties here, which are going to make a lot more sense talking about them with these bushings than these boots. So these were the original ones. I'm like, well, can I just 3D print them to look decent? Which means they needed to be face up, so we'll just use 2 and I don't know, glue them together. Did not end up going this route, but basically I used these to test the stiffness rate. And so, well, I guess I got to turn it around anyways. So what we've got here is my setup. So this is a 1,500 pound scale. This is the OEM bushing. This is a test fixture. Ignore that, that doesn't need to be there. And so I can actually measure the rate of the bushings. I have spots here for measuring with the caliper to get very accurate displacement. And I move it, measure the number, move it, measure the number, and what I'm able to do is produce those rate curves. And so then I'm able to take these inside, you know, some cans. It's kind of a tight squeeze, but I'm able to take these, put them in cans, put them in this fixture, and then I can measure how stiff this stuff compares to the rubber. And so I was able to get rate curves for these. And so they were obviously way stiffer than OEM, which is not exactly what we wanted. So we had to add some voids. And so I added these voids here to make it a little bit softer. Next was to test dimensions to make sure that the bushing stays attached to the inner metal. And so this is just a smooth sleeve, and you can see it takes a pretty decent hit to move it. And I don't believe this is under much compression. And so, yeah, this was originally hey, I went through a couple trials for how to bond the TPU to the aluminum for durability and NVH reasons. The reason you want that is what's up? What is that?
Brought you apple crisp.
You brought me apple crisp. Thank you.
Welcome.
Did you just bake this?
Yeah. It's been done for like 10 minutes. Could be toasty.
Oh, very good.
Thanks.
It's so hot.
Yeah.
Do you have some water?
Yeah. I have ice cream freezing for dinner.
Okay. For dinner?
Yeah. Well, like dessert.
Dessert?
Yeah.
Okay. Thank you.
Um,
Love you.
that's not even me.
All right. So the goal was to get the TPU to bond to the can because, for example, when you pull on this, the only reaction force is going to be on this side because you're squishing this material, because if it's not bonded, it's going to pull away from the other side. Just like the bushing will pull away from the can, right? And that's why OEMs use bonded bushings, because you can basically run a material that's half the stiffness to get the same stiffness in the end. And what you get from that is lower frequency isolation. So this is the ride direction, so the engine's going to be bouncing like this, and this reacts the torque. And so if you're just going that direction without a bonded bushing, let's say the material is 100, it's 100 newtons per millimeter effective stiffness. So 100 newtons of pushing, it moves 1 millimeter. With a bonded bushing, I'm not saying that the right way. Let's just say the stiffness value, the unit, it's unitless, it's just 100. So with a bonded bushing, let's say if it's 100, I pull on this, it's reacting in both directions. So I get 100 stiffness from the compression, and I get 100 stiffness from the tension. If this is a polyurethane bushing that's not bonded, or a rubber bushing that's not bonded, I'm only getting that 100 from the compression side. And so what we really care about is having the final rate be 200. So for an equivalent polyurethane bushing of the exact same, or doesn't matter, an equivalent unbonded bushing that needs to have the same functional stiffness has to have a unit stiffness of 200, because it's only going to be compression in each direction. And so what happens is you get stiffer everywhere, and so you're not going to isolate low frequency stuff as much. And so what I ended up coming up with is there are some adhesives that you can, some very, very limited select few adhesives that you can get to bond to polyurethane and aluminum well. What professionals do is you sandblast the aluminum, you immediately clean it and immediately put a sealer on it so the aluminum doesn't oxidize, but the sealer will bond with the polyurethane, and it also bonds with the aluminum a little bit. And so you have your inner and outer metal, you have whatever you're making, and then you inject the polyurethane onto that and bake it, and the heat will catalyze the sealant, and you'll get a bond to the aluminum that is, or steel that's as strong as the parent material. So it's a true bond. But you need an oven, you need toxic chemicals, you need a lot of really expensive stuff, and I wanted to get around there. So I tried a bunch of epoxies. I built these little test fixtures. Well, unfortunately I'm not sure where they went, but they were basically 1-inch polyurethane plugs. So I would descale the aluminum, wash it with acetone instantly, and then I'd put the epoxy on, and then I'd rough up the polyurethane one square inch, and I'd bond it to it. But then also what I did was I just basically heated up the other side of the metal, and then I sanded it and cleaned it real quick, and then stuck the polyurethane to it and held it until it cooled down. And wouldn't you know it, I actually found that to be the strongest bond out of all the epoxies. I even called 3M, and I got a really good reference from 3M, and it's great under low dynamic loads. What a low dynamic load is it's a cyclic loading, like push, pull, whatever, that is significantly lower than the yield strength of the bond, but when you start getting up higher to the yield strength of the bond, it doesn't have much fatigue strength. So we tested that and came up some pretty good results. So what's cool about this, one thing that I had to do to improve the bond was, instead of having these kind of come outward because it looked cool, they now go inward. And what that does is it prevents the urethane from peeling off the leading edge. So it creates it gets rid of the stress riser that you get right here. And that actually made a huge difference in bond strength. And I also had to make it a little bit softer because these were still really, really stiff. And what's interesting is, so this one it's smooth bore. Both of them are smooth bore, just like these. There is some compression, but you know, you hit these and they don't really want to move. And that is just with well, it's an overmolded diameter. And then I'm probably being a little overcautious here, but I can talk about that later. So I didn't want these to slip out, and what's funny about powertrain mounts is even if they slip laterally, you have so many mounts, your powertrain's not going to go anywhere. But I don't want squeak. That's the big thing. I don't want squeak. So we redesigned it again. Now we've got ridges on the outside, and we've got ridges on the inside. I did do some testing with 3D prints, which yielded a lot of explosions of urethane. The carbon fiber nylon is actually a really viable solution for bushing cans. You just need a little bit more space to work with than that. And so this is kind of where we ended up. And so now we get into another one of the issues that's maybe not necessarily to forging a TPU print, because it is not necessary for the forging process, and if it's not a bushing, if it's anything else, this really doesn't matter. But what really came to matter through additional testing is there's an interference to these diameters that I spent some time coming up with empirically what a good interference was, and then backing that up mathematically so I can correlate it to future projects. And the balance between that is more compression's better because it's less likely to stick. It's more likely to stick, but less compression or too much compression means that you're going to destroy this thing, shearing it off going in. And again, for example, that's the difference there. It's this is also a much larger diameter than this. And the way I handle that is, this was the exception when I was talking about overdoing the dimensions, is every dimension in this is accurate except there is a radial offset in the model from between this guy and this guy, and you can see that the diameters are very different. And I think maybe to make it a little bit more apparent, if I take one of the molds, well, actually, yeah, that'll work. Just these, so you can see how different those diameters are, right? And so that became very important, is there was a balance between having enough compression that you're pretty happy it's locked in, but not having so much that you shear the bushing on installation. And so I was pretty dead set on this, but after beating up a few and burning a few, I did realize there were some faults to my design, which the Honda guys already knew, of course. So my mistake was, I was like, hey, let's make sure that it's soft in this direction and stiff in this direction. So I figured out how much material I needed to be able to pull that off. That was just a little bit stiffer than this guy. And so I ended up here, but what happened after some durability testing is this does not have a higher shear strength or elongation than rubber. So I'm sitting here looking at this and I'm like, well, there's less material here than this, which means that the stress on the inside is going to be a lot higher on this than this under the same conditions. You can argue it's going to move a little less because it's a little stiffer, but there's a hole here because when you push, you need volume to fill, or this stuff will want to squish out this way and start shearing itself. And so you're using these two legs that can displace that way and in on themselves. And that's the case here too, but they're just too thin. And then you're relying on these for a majority of the strength. And so you could argue, well, you could turn it sideways then. Well, oh, you know what? This is actually this is how I intended to run it. My bad. I was trying to be soft and ride. So that same thing still applies, but there's just a lot less material. And when you squish on this, it has to go left or right, or up or down, I guess. And so due to chaos theory, you just end up getting inconsistent compression, stretching. And it's not ideal. So I redesigned the bushing and I was like, you know what? Let's just go with what Honda has and we'll go from there. And so we ended up with this guy, which it's pretty obvious where the inspiration came from. And so I believe, yeah, this is post forging. For example, this is the solid race bushing, and this is the difference before and after. Now, you're asking why these are different colors. Well, I only meant to print 2 of these in this color, but the plate has 7, and I forgot to cancel the other 5. So then I just had to keep grabbing random material to finish the print. So you can pick either color, it doesn't matter. But that is a good example of the quality before and after forging. And then of course the final bushing you have is this guy. And so you can press it in there. You can kind of see the displacements from the squish. You can see where it bows a little bit. And yeah, that's oh, I guess the more complex mold, we can go there. Alright. Alright. So this is how this mold works. Again, you have to be able to design the mold so it can be assembled and disassembled easily. So that's what we have here. So the bushing, fresh out the printer, goes down onto this. Now I've got holes drilled so that I could put bolts in so that these don't snap off. This stuff is wildly stiff. So here's a test one with not great filament without the bolts. And you can see they're pretty stiff even without, but I'd rather be safe than sorry. So for example, this one mold, this is $20 in filament. For this stuff is about $200 a kilo. So considering the assembly and disassembly, I don't want to have to slide the bushing out of the mold, so I had to make these walls. And there is a chamfer inside here, and you can see the other chamfer right there. So as you squish these together, they will actually pull in on themselves and tighten up even more. So it's a lot harder to assemble pre-bake. Okay. Obviously these center pieces are still in here because they have to be pressed in and out. So you press those in, but everything else is done by hand. And then this guy, before it's baked, is extremely hard. You actually have to hammer it down or put it in the vise to get it to go down. And then you put the final piece in. And so you go over, I have a setup on the press where I can put the nut and the bolt in, and plates come down. And so I squish it together in the press. Usually it's got, I don't know, 3 or 4 millimeters before I press it. And so I'm pressing about 3 or 4 mils, and then I tighten the nut and bolt down on these guys. And once that's tightened down, they're ready to go. And then I just put them on I have a whole bundle of these guys. So I can do 8 at a time. And another feature of these is I have holes here for these little M4 bolts. So I'm not prying on the mold. I just put these in afterwards. They're obviously not supposed to be in there now. And I can just run a screwdriver in there and it pulls them apart. And what's nice is when they cool, they still do shrink a tiny bit, even though they've been compressed. So the whole mold just comes right apart. Now there are better materials you could use for this. I would prefer to run the hottest materials that I can so that I can run the oven at higher temperatures. And so what I'm going to do moving forward is, instead of making these end plates fully carbon and this outer ring fully carbon, I'm going to do these out of aluminum. Still use these inside pieces out of the carbon along with this inner feature. And the reason I want to do that is if I go higher temperatures, so this one I went a little too high, you can see it deformed just a tiny bit, but I don't want them to wear out. And so if I can just make the interface features, the printed features for high detail, I can use the aluminum for structure. Under compression, these aren't going to move around a whole lot, especially if they have, you know, the metal in there holding it. And so I probably won't need to leave them overnight, and I will get a little bit better finished quality out of it, a tiny bit. But I think using send cut send for end blanks and stuff like that, it can be really cost effective. And actually I'm betting it's cheaper using aluminum and the 3D print than just fully the 3D print, because the solid stuff can get pretty expensive. So yeah, that's kind of it for the forging stuff. I went over why I prefer to use TPU over polyurethane in general. Why I do think it's better than cast poly. The issues with compressing it, not only due to the fact that even 100% infill isn't 100%, and just also with the kind of the compression forces that you need to be able to calculate. Like here's a really good example. So, oh, I forgot a step. So once these guys are ready to go, I prep the inside in a way to descale it, and I assemble them very quickly, because aluminum really starts to oxidize in about 30 seconds, so you want to make sure that you've got enough time to just run straight through it. Also, I guess I didn't point it out, but these are where those come from. So it's 6061 aluminum to get these guys. This little nubby helps prevent the insides of these from getting caught in shearing, and then it just sticks out the other side. So that's just an installation tool. Yeah, and so once they're assembled and installed, I then actually apply heat to the outside of the can, and then I blow heat through the center of the metal. And what that does is, with the fresh raw aluminum and the prepped clean poly, is not only do I have the interference from the ridges, but now I've actually bonded the poly to the aluminum in the strongest way that I was able to find experimentally. And I used a lot of really expensive adhesives. I was on the phone with 3M, tried some Parsons, but what's cool is this one has no adhesive. It has no ridges on the inside or the outside, so this is smooth bore, and it has that much retention. So I am not concerned about these guys coming loose and squeaking. And because they're over molded. For example, if this is 2 millimeters larger than the interference surface of the bushing, that means it can displace 2 millimeters before it starts to lose spring force from the opposing side. So between kind of the over volume mold or the interference, along with using the heat to bond it to the fresh raw aluminum, you end up with a pretty durable bushing, because what can happen is these will hollow out if it's just a regular poly bushing. I'm not sure if I have any. Well, I don't have any. So did learn one issue, not to drop your stuff, so I kind of messed that up. Giving the customer a $50 discount. But yeah, so that is, man, I really like how these came out. They'd be a little more matte. I do not believe I cleaned the wax off after they came out of the mold. Oh, I did forget that. Holy bejesus. Last thing. So, before these get used the first time, wax. Cover the whole thing in wax, and then use a torch to melt it in there. Otherwise, you're going to have a damn hell of a time trying to get this stuff loose. So don't forget the wax. But otherwise, I think I covered everything.